Hello, Science 30. This lesson is going to be on fields, and I'll talk about gravitational fields, electric fields, and magnetic fields. However, I might split it up into a couple of lessons if this seems to be going a little bit too long. So at least for sure, I'll talk about gravitational fields in this lesson. So first of all, what do we actually mean when we're talking about a field? It is referred to as the sphere of influence around some sort of a source. So I can only do this two-dimensionally, but if we do have a source in the middle here, and then if we have a ball, a sphere, it's everywhere outside of where that source is, where the effects of that source can be felt. So that is what we mean by a field. So any object that has a mass, any object that has a mass. So we can be talking about big, huge things like planets and stars, or tiny, tiny little things like atoms and even subatomic particles. But if they do have a mass, then they do generate a gravitational field. Any charged object, anything that has a charge, whether it is a positive or a negative charge, they will generate an electric field. And magnets as well, they will generate a field around that magnet, what is referred to as a magnetic field. And with magnets, rather than positive and negative, we usually talk about the north and the south poles. So for each one of these fields, there does need to be a source. So when we're talking about gravitational fields, that source will be a mass. For electric fields, it will be a charge. And for magnetic fields, it would be a pole. There is a direction associated with these as well that we'll chat a little bit about. And there are strengths of these fields that we're going to get into some calculations with, at least with the gravitational and the electric fields. So first of all, let me just use a little bit of analogy though. So if we were sitting in a classroom, how well you're able to hear me, and I'll just use a capital H for L. So what determines how well you can hear me? Well, a couple of things. It could be many, many things, but a couple of the things that I'll mention here. First of all, how loud I actually talk, the loudness. So the louder I talk, the more easily you can probably hear me. And I'm just going to give this a symbol, and we'll just call it a capital L for loudness. So the louder I talk, the better you can hear me. So what we can say is that there is a direct relationship between how well you hear me. This here is the symbol for proportional to. Proportional to. So how well you hear me is directly proportional to how loud I talk. The louder I talk, the better you can hear me. So kind of a one-to-one relationship there. Another major factor that determines how well you can hear me is how far away I am from you. So we'll just say the distance, and I'll just use the symbol D for that. In this case, it's the opposite relationship though. This is what we call an inverse relationship. So now we put 1 over this proportional symbol. Now the further you are away, the less you can actually hear me. So there's an inverse relationship between those. So if we just turn this into an equation, and you'll see where this is going in a minute, how well you hear me is equal to how loud I talk. But the further I am away, the less you can hear me. So we put that in the denominator. As it turns out, what has a greater impact is how far away you are. So if you move a distance twice as far away, 2 times further away, I would need to talk 4 times louder. So what I then need to do in the denominator for the distance is I need to square it to kind of show that that has a more of a dramatic impact on how well you actually hear me. So this analogy that I'm giving you here, it may or may not actually be the case, but I did want to show you the connection between this and a couple of equations that we're going to be using, calculations that we will be doing for gravitational and electric fields. So a little bit of theory here, first of all, going all the way back to Sir Isaac Newton. It was in 1666 that so the story goes, he was sitting underneath an apple tree and sort of pondering, when this apple falls, why does it always fall straight down? Why doesn't it fall to the side or go up or anything else? It always falls straight down. So this is where he began to come up with his mathematical equations and the universal law of gravitation. And by universal, that means it's not only underneath his apple tree, it's anywhere on the earth, and it's anywhere in, as far as we know, the entire universe where this law does apply. So in 1687, this is what he did come up with. It's kind of wordy, but he says every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This is actually what I just tried to show you with that analogy. So when we're talking about the attraction, so the force that he's talking about here that they're attracted with, the force is directly proportional to the size of the masses, so the product of their masses. So the mass directly proportional to the mass, but the force is inversely proportional to the square of the distance between them, so d squared. Oops, d squared. Okay, so that's very kind of similar to what I showed you on the previous slide. So let's just turn this into the actual equation. You don't need to memorize any of these symbols that I give you here because it is in fact in your data booklet. I'll show you in your data booklet where you can find all of this in a minute here. So for what we call gravitational field strength, that's what we're going to be calculating. What is the actual field strength, the area around that mass where the effects of this gravitational field can be felt? So if this is our mass that we do have here, then the direction of pole is always going to be toward the center of a mass. It's always toward the center of a mass that we're going to be talking about. So I'll show you another picture in a minute here that's going to in fact have two different masses because it does need to be between two different masses. But what this does show here is the direction of the gravitational field, and it is always toward the center of any mass. Few other symbols. This arrow up above, by the way, that just means it is a vector. So in other words, there is a direction associated with it. This G down here, there are different kinds of forces. This one is specifically due to gravity that we're talking about. So capital F is for force, and this is specifically the force due to gravity. R is the distance between the centers of the different masses. Again, I'll show you a picture in a minute here. And we do need to have what is called a gravitational constant that, again, as far as we know, this is universal anywhere in the entire universe. This is a constant that we're going to apply to this equation. Really small number that we have here. Exponent to the negative is a really small number, 6.67 times 10 to the negative 11. Units are important, and I'm going to be emphasizing that when we do get into a couple of calculations here. So this is just showing that proportionality. So the force is directly, again, proportional to the two masses. So the bigger the masses, the product of the two masses, the greater that force due to gravity is going to be, and inversely proportional to the distance between them squared. So once again, as with my analogy, the distance between them has more of an impact on the force than the actual size of the masses. So let's take a look at this picture here. All of these arrows show the direction of the gravitational field, and it's always toward the center of the mass. So for this M2, the smaller sphere, it is toward the center of the mass. Same thing with the red sphere. It's toward the center of the mass. Both of these are attracted to each other, but because M1 is larger, the net gravitational pull will be more toward the larger one. But yes, the smaller one is attracting the larger one as well. It's just that there's more of an attraction, more of a gravitational pull from the larger mass, which is M1. And it also shows in here, and this is also kind of important, it is from the center of each one of the masses. So what we use for the distance between them is r. So r is the symbol for the distance between the center of the two masses. So this is an equation here that just shows that proportionality, and we've also stuck in this gravitational constant that we'll have to use for all of our calculations. Another equation here, force is also equal to the mass of the object times this here, which is gravitational field strength, but it's also acceleration due to gravity. So force is equal to this. Force is also equal to this, which means these two are equal to each other. And that's what it's showing here. So now that we have this equivalency, we can cancel a few things out here. We can cancel out one of the masses on each side. And then what we're left with is this tidied up version of the equation. This is the one that's in your data booklet. This is the one that we're going to use. And this is the one that is the calculation for what is called the gravitational field strength. The strength of that particular gravitational field due to the source mass that we have, which is typically going to be the larger mass. So I'm going to exit out of here for a minute, and I'm just going to go to the data booklet and show you in the data booklet where you can find some of this information. So data booklet that we have. Okay, so I'm first going to point out that on the first page here, page 1, it does give you all of these prefixes. So if you don't remember what a giga is, it tells you that it's 10 to the 9. If you don't remember what a micro is, it gives you the symbol. It tells you that it's 10 to the negative 6. So you don't need to remember any of that information. It is given to you right there. You don't need to know any of this stuff on kinematics and dynamics for Science 30. These are all the equations that we're talking about right now, though. So gravitational and electric fields, we have this equation here that I just briefly talked about. But the big one for us to use for Science 30 is this one. So again, G tells us what it is. It's the magnitude of the gravitational field strength, and it gives us the units, newtons per kilogram. Gravitational constant, capital G, you never need to remember that. It's given to you right here in the data booklet. It tells you that the mass is in kilograms. It tells you that R is the radius or center to center distance, and that is in meters. So if you're given a number in kilometers, you do need to convert it into meters. We're always working in kilograms. We're always working in meters for these calculations. Down below as well, I'm also going to point these out. The mass of the Earth, they give it to you. So it may not be given in a question because it's in your data booklet. Same with the radius of the Earth, the mass of the Sun, and a couple of other numbers that they give you there as well. So all of that information, it is given to you in your data booklet. You just need to know where to find it and realize that it is available for you, and you don't need to remember any of that information. So back to our lesson here then, and let's get into some of these calculations. So calculate the gravitational field strength with you, or me, standing on the surface of the Earth. I find it's always useful to draw a picture of what it is that we're trying to do. So this here is Earth, and we're talking about you standing on the surface of the Earth. So we have two different masses. So we'll call this M2, we'll call Earth M1, and we're talking about the distance from the center of the masses. So the distance from the center of the Earth to the center of you, that's going to be the radius that we're talking about. M1 compared to M2, it's not even close. So it's so much bigger with M1, the mass of the Earth, that we're just going to ignore the mass of you. It's not going to make any difference in any way whatsoever. So if you go to your data booklet, you can write down the equation that you need right away. So the gravitational field strength. So once again, that is going to be the lowercase g multiplied by the capital G gravitational constant times the mass, that would be the mass of the Earth, and divided by the distance between the centers of the masses squared. Whenever you're doing calculations, this is what I always ask for. You might recall this from previous science classes. Grasp. I'm usually not too concerned about dP, but I am concerned about all of the others. So the G, this is the given. What is the given information that you have? And you might say, well, you don't have any information that you're given here. But remember, in your data booklet, they do give you some of this information. So they tell you in your data booklet the mass of the Earth. So I'm just going to write this down as M, and I'm going to put a big E for the mass of the Earth. And it is 5.98 times 10 to the 24. Always write the units, and it is kilograms. Make sure it's in kilograms. If it's not, you need to convert it into kilograms. We also saw in the data booklet that it actually gives the radius of the Earth, and that is in fact what we want here, is the radius of the Earth. So in your data booklet, it says that it's 6.37 times 10 to the 6. Again, it is in meters, so we don't need to do any sort of a conversion there. Also in your data booklet is another given, the gravitational constant. So it is the 6.67 times 10. Don't make a mistake here. It is negative 11. And the units are newtons times meters squared per kilogram squared. So we'll see in a minute why I always have you write down all of the units and the reason for that. So now we have the given information. R stands for required. What is the question asking is all it is. And the question is asking for the gravitational field strength. So this is our equation. We've written down the equation. Sometimes you need to rearrange the equation. In this case here, there is no rearrangement. This is what we're solving for, which is what's on the left-hand side. You need to write everything down. Don't make any mistakes. So we have 6.67 times 10 to the negative 11. Again, write the units down, and this is where we're going to see why we're writing the units down. Meters squared per, I'm just going to write a little bit different so it's clear that we're dividing by the kilograms. Okay, we're going to take that and we're going to multiply it by the mass of the Earth, which is the 5.9. It's actually 5.98. 5.98 times 10 to the 24 kilograms. So why do the units? Because now we can see that this is actually going to cancel out with 1 of the kilograms that we have in the denominator. Here it's in the numerator, here it's in the denominator, so they cancel out. Now we're going to divide this by the distance between the two masses. So that's our 6.37 times 10 to the 6 meters. And then we're squaring this. So we're squaring the entire thing. So that means the meters are squared. And up here we have meters squared. So the meters are going to cancel out with these meters squared here. What are we left with for our units? The only thing we have left are newtons and 1 of the kilograms. And if you take a look in your data booklet, those in fact are the units for the gravitational field strength. So this just shows us that we set everything up correctly. Now you need to be careful when you're plugging these numbers into the calculator. What I recommend you do is put this number in and press enter. Then go times, put this number in and press enter again. Then usually what you need to do is open up brackets when you're dividing by. Okay, so go divided by, open up some brackets. However many brackets open up, you need to make sure you close them at the end as well. And we're also squaring that at the end, so you can't forget about that. I'll give you a clue here for how to estimate an answer and to make sure you're on the right track. If we just take a look at the exponents, a little bit of a math trick here. So if we take the exponent for our first number, we're multiplying it by this number here. But in terms of the exponents, we can sort of estimate what that number is going to be by adding them together. Okay, so in the numerator, so minus 11 plus 24. So that's going to give us 13. In the denominator, we have another exponent. And the way that it works, if we're taking this 6 and squaring it, it's like you multiply those two together. So in the denominator, our exponent is going to end up being a 6. Now the way that you figure out overall what your exponent is going to be is you take what's in the numerator and subtract what's in the denominator. So 13 minus 12 means that we're going to get a number that's going to be fairly close to 1 for that number. Okay, so something like 10 to the 1 is what we should be getting. So this is a kind of a good idea if you understand that, to make sure that with your final answer, you are on the right track. So when you do plug all of these numbers into the calculator, this is what you do actually get. You get 9.82987, and then there will be a whole bunch of other numbers as well. And this one here, there isn't an exponent. This is the actual number that we do have. And the units, again, are going to be newtons per kilogram that we do end up with. So this number here is, well, exactly what we kind of estimated for what the answer will be. So this is our acceleration due to gravity, which is actually the gravitational field strength. So if you take a look in your data booklet, it does give you a number 9.81 meters per second squared, acceleration due to gravity on Earth, and that is actually the same as the gravitational field strength. For questions on quizzes and exams, this might be a numerical response question where you have 4 boxes, and they might say record your 4-digit answer. So you need to get the right answer, you need to round it correctly, and you need to fill in these boxes correctly. So 9 is a digit, 8 is a digit, 2 is a digit. Decimal is not a digit. So actually for this one, they would be asking for a 3-digit answer. The decimal would go in this box here, and that's not a digit. All of the other ones are. So it's 9.8, but now you need to make sure that you take a look at the next number, because this one gets rounded up to a 3, and this would be your correct answer, 9.83 newtons per kilogram. So I think I'll stop there with this lesson. It's getting kind of long, so we'll keep it at that for the fields so far. So that is for the gravitational fields, and I'll get together another lesson, a separate lesson for you, which is going to be on what we see on the screen right now, electric fields and also magnetic fields.